Okay, this video is Force and Motion from Unit P2. It's topic 3. It's the second video of 2 for this topic. So the first video dealt with distance time graphs and velocity time graphs. This video deals with how to describe motion using forces. So in general, this is something that doesn't really get done that well by GCSE students. If you're asked to describe motion, what tends to happen is you just describe motion, but you don't talk about the forces, and it's really important that if you want to gain good marks, you have to talk about forces. Now, underpinning all of this would be Newton's. I'm going to talk about Newton's first 2 laws. So Newton's first law was, and this is Isaac Newton, his first law that he gave us was that if you've got an object, let's say a box on the floor, if there's no overall forces acting on the box, the object will remain at rest, which just means it will stay still, or continue to move at constant velocity. Okay? Which this second part is really important, because what it means is if an object is already moving and then the forces are balanced, it will just continue to move at constant velocity. It won't stop. It just carries on moving at the same velocity. And when I say if there's no overall forces, you could have forces acting on the object because the object has a weight. There will be a reaction force from the ground pushing up. You could even have a ropes wrapped around the box, and it could be getting pulled this way, and it could be getting pulled this way. But as long as them forces balance each other, and them forces balance each other, then overall you've got no resultant force. Okay, so just say that again quickly. If there's no overall force, because the forces balance each other, then an object will stay still or will carry on moving at constant velocity. Okay, and the second law that he gave us was, well, if we have got unbalanced forces, that will lead to acceleration. Okay, so if there is an overall force, let's say, for example, if this force suddenly got a bit bigger, then there will be an overall force in that direction. Then he gave us this equation: force equals mass times acceleration. Now, we tend to use Newton's first law to describe motion. Well, actually, we'd use both of them to describe motion, but when it comes to calculations, it's the second law that we'd use. Okay, so if you're given numbers in a question, it will be the second law, and you'll use this formula. Right, so let's pick an example. Let's go with a person jumping out of a plane. So if we said there's the plane, and the person's just jumped out. So the first stage, let's say they're here. 10 seconds later, they're down here. 10 more seconds, they're down here. Okay? So, what we need to think about is the forces involved. So if we're going to talk about this, how the speed of this person changes, or the velocity changes, we need to think about the forces involved. And there's only 2. One is the weight of the person, and one is the air resistance acting on the person. Now, the weight doesn't change, the person doesn't get heavier or lighter, so I can already pre-draw that force in. I'm going to draw it that big. And you notice that the length of the arrow stays the same, and that the arrow has been drawn on the person, not sort of, I didn't do this, which I see all the time, just over there somewhere. That's not how you do it. You draw the arrow on the object itself. So there you go, starts on the object. There's the weight. Same size arrows because the force of weight is exactly the same. Now, You'll know what air resistance is because if you've put your hand out the window of a car, especially if the car's going fast, you'll feel a big air resistance because the faster you go, the bigger the air resistance is, okay? So, if the person's just jumped out the plane, they're not going very fast, there's only going to be a little air resistance force, so I'm only going to draw it that big. I'll label it AR, okay? A little bit later, the person's going a bit faster, so I'm going to draw the air resistance force a little bit bigger, AR. And let's say that this might be a minute into the fall. Let's say they're at terminal velocity, so this time the air resistance is the same size as the weight. This is terminal velocity. Now, terminal velocity is when you're going as fast as you could possibly go. Now, all cars have a terminal velocity. Okay, so when the car is, you're trying to make the car go as fast as you can, you're in the highest gear and you've got the accelerator pedal right down, there'll come a point where you'll go as fast as you can and you can't go any faster. And the only way to go faster would be if you could push a button and change the shape of the car to make it more streamlined. And if you made it more streamlined, the air resistance force would get smaller, and so you'd be able to go a bit faster. But obviously we can't push a button and change the shape of a car, so that's why car manufacturers, they spend millions of pounds, especially Formula One, in Formula One or in supercars and things, to try and make the body of the car as aerodynamic and as streamlined as possible, so that this air resistance force is as small as possible, so the car can go as fast as it can. Right, now if we look at these forces, there's only one situation where the forces are balanced, and that's this one. So if we go back to Newton's first law, he said when the forces are balanced like this, then it'll either stay still or continue to move at constant velocity. Now, that person's not going to stop in mid-air. The forces are balanced. This is constant velocity, like we've just said. Constant velocity. Okay? Now, this one, we've got a resultant force, and the resultant force is obviously a downwards force because this arrow is longer than that arrow. And just looking at it, I would say if I took away that length of this arrow, I'd end up with a resultant force. I'm just going to draw it to the side here, about that big. Okay? And if I looked at this one, I'd say now we're going a bit faster because this is about 10 seconds into the flight. When you're going a bit faster, air resistance is a little bit bigger there than it is there. So the resultant force now is a bit smaller. It's only about that big. So I'm going to just move them out the way because they shouldn't really be there. We shouldn't draw arrows in mid-air. So what we'll say here is we've got unbalanced forces. So unbalanced forces means that there must be acceleration. Okay? And would we say that acceleration was large or small compared to this one? Well, I'd say in which case are the forces, sounds a bit more unbalanced, that doesn't sound right. In which case have we got the biggest resultant force, in this one or in this one? And the answer is in this one. Okay, so we're going to have a large acceleration. Yep. And in this one, the forces are becoming a bit more balanced, so that the resultant force isn't quite as big, but we have got unbalanced forces. So we have still got a small acceleration. Okay, so we've used Newton's laws because we've been able to say unbalanced forces give us accelerations. We know if we've got a large resultant force, it's going to lead to a large acceleration. If we have got balanced forces, that will give us constant velocity. Now, I'm just going to couple this in with a velocity time graph. So I'm going to call this stage 1, stage 2, and stage 3. Okay. Now, if you remember on your velocity time graph, and if you want, you can pause this if you want, and you can try and draw a velocity time graph for this scenario and try and label it stage 1, stage 2, stage 3. But here's the answer. Right, when you jump out of a plane, you start there. You're not moving at the start. When you jump, your speed or your velocity increases, okay? And it increases to a point where you end up at terminal velocity. Now, terminal velocity is constant speed, and you should remember the constant speed is straight across. So what will happen is it will go like this. Okay, stage 1, stage 2, stage 3. Terminal velocity, constant velocity. Yep. Stage 1 has got a large acceleration. How do I know it's a large acceleration? Because the gradient is steep. Well, based on this, we said it was going to be a large acceleration because there was a big resultant force. So stage 1, large acceleration. Stage 2, smaller acceleration. Stage 3, no acceleration because we're in constant velocity. Okay. Right, now that's just jumping out of a parachute, jumping out of a plane. Sorry, I didn't talk about a parachute when you pull a parachute, which I'll go into now, but it's pretty much going to be more of the same. So let's think about now. If you are at terminal velocity, so let's call this stage 3 again, and then you pull a parachute. What happens next? And then let's just draw them again with the parachute. So stage 3, I'm going to do this quickly because this video is getting quite long now. There you go, there's your weight, same size all the time. Air resistance, if you remember in stage 3, was the same size as the weight. Now when you pull a parachute, what happens is suddenly the shape changes of this object falling through the air, which was the person, and air resistance goes absolutely huge. Much bigger than the weight. So what happens now is we've got a resultant force, but actually the resultant force is an upward resultant force. So going off Newton's second law, unbalanced forces are going to lead to acceleration. Well, yeah, strictly speaking, it is an acceleration, but it's actually a change in velocity, but it's not speeding up, it's going to slow down. So this person, when they pull the parachute, they're going to decelerate. It's a change in velocity, okay? So when they get slower, what's going to happen to the size of air resistance is that as you pull your parachute, air resistance shoots up, causes you to slow down, and as you get slower, air resistance starts to get smaller and smaller, and you reach another point where air resistance is the same size as weight again, and you've reached another terminal velocity. And that terminal velocity will be a lot smaller than the terminal velocity before the parachute was pulled. This is why car manufacturers will get the cars to be as streamlined as possible, because that will give them the highest terminal velocities possible. Okay, I'm going to stop that there.